Okay, so let me start by mentioning something that I meant to mention in the last lecture. And then we'll spend the rest of the day talking about currents. So I mentioned that there are many examples of minimal submanifold stationary varifolds with singularities. So let's look at an example. In order to do this example, I've got to recall a couple of things. If you have a function, capital F, going from an open set U into R, and it's, say, at least C2, let's say C2 for our purposes, at least. And then you look at the level set. You look at the zero level set, and you only consider the points where the gradient is non-zero. This is the gradient in U is contained in n plus 1. So this is a bit of a different situation with in Rn plus 1. And this is the full gradient in Rn plus 1 of fx not equal to 0. Now you remember we discussed that when we were talking about the co-area formula, and we pointed out that the implicit function theorem implies that this is either empty or sigma is a C2 submanifold, is an n-dimensional C2 submanifold of Rn plus 1. Remember that? And furthermore, so we'll forget this case, so assume that this is non-empty. So assume that. So that means this case is out, and we simply can say sigma is definitely an n-dimensional C2 submanifold of Rn. And not only that, notice that this gradient gives you a unit normal also. Gradient of f at x divided by the length of the gradient of f at x is a continuous unit normal for this. In fact, it's a C1 unit normal. Unit normal for this submanifold sigma. So that's good. So that's, I just wanted to remind you of that because we're going to use that here. So in this example, we're going to take F, we're going to be working in R2n actually. So we're going to let points in R2n be denoted xy. Where x and y are individually in Rn. This is R2n. And take this special case when f in this discussion, fxy, is just the polynomial length of x squared minus the length of y squared. So let's see if we can apply this, this fact here, first of all. So let's do that. So let's take the gradient of f. Well, to get the gradient, it's better if we normalize by taking a half. This avoids getting a lot of ugly 2's floating around. And then the gradient of f at xy is just x minus y. That's not equal to 0, except at 0. So this is not equal to 0 on R2n minus 0. So that means thus sigma, by this fact here, that implies that sigma, which is the 0 set of f, that's the set of xy in R2n minus 0, such that mod x squared equals mod y squared. That's the zero level set of this function. That is a C, well, it's C infinity, of course, because this is a C infinity function, so equals a C infinity submanifold. I mean, this result is general. Remember, if this is CQ, then correspondingly, this becomes a CQ submanifold. So in particular, if it's C infinity, then you get C infinity submanifold of n-dimensional. Oh, now, in this case, let's see, we're in R2n, so it's 2n minus 1 dimensional. C2 submanifold. And I claim this is a minimal submanifold. Sigma is minimal. Now, before we do that computation, let's see if we can work out what this looks like. Notice that this is homogeneous, so it's invariant under multiplying multiplying both coordinates by a scalar lambda. So it must be a cone. It's a cone. So this is it's a 2n minus 1 dimensional cone. Leaving out the origin, of course, because remember the origin is the place where the gradient is 0. So, and let's see if we can work out how it intersects the sphere. Sigma intersect with the sphere. Now let's see. We're in R2n, so we're intersecting with the 2n minus 1 dimensional sphere. Well, that's the set of points in Rn, set of x, y, a set of points in S 2n minus 1, a set of points x, y, such that x squared plus y squared equals 1. And mod x equals mod x squared equals mod y squared, or mod x equals mod y. Well, notice that's the Cartesian product of two spheres. In fact, you can write this as Sn. Let's see, the spheres are n-dimensional, that's right. So this is n minus 2 dimensional, so it's Sn minus 1 with radius 1 on root 2, because you get a 1 on root 2 from each of these. Cartesian product, S minus n minus 1, 1 on root 2. So that's what the intersection was. So in other words, the picture is, this is sort of a torus in the sphere, higher dimensional torus in the sphere. So the schematic picture is something like this. It's a bit hard to draw because we can only draw it in 3 dimensions. So it's, but anyway, you've got this submanifold Clifford torus, and you're taking the cone over that to give you sigma. So that's what the thing looks like. Now I'm claiming this is minimal, so let's check that. We've got to compute the mean curvature. Well, that means we've got to compute the second fundamental form, right? So that involves computing the, you remember how we computed the second fundamental form? We had to take an orthonormal basis of the normal space. Well, in this case, that's easy because there's only one vector, and the normal space is one-dimensional. It's just this normal vector. So this is, let's call this nu. So, so the second fundamental form in the direction at a point x, y, in the direction tau eta, remember by definition is minus the directional derivative of nu in the direction tau, dotted with eta, and then multiplied by eta. That was our definition of second fundamental form. Now, if you work this out, I'll leave you to check my calculation here. If you work this out, you'll find that you get the following expression. You get minus the sum tau, let's see, gij eta j tau I times nu, sum from ij equals 1 up to L. Yeah, that's not right. Sorry. We need to work this out a little bit more, so let's do it. Okay, so nu is grad f over the length of grad f. So d, so this is tor ij. Well, remember the expression for this. It's the one of the ways of computing this would be to use these are tangent vectors, so you can use the matrix of the orthogonal projection onto the tangent space. So Eij is the matrix. It's delta ij minus nu I nu j, where ij goes from 1 up to 2n, up to 2n. We're in R2n here. So this is Eij tor I, let's see, Eij dj dj nu I times eta I times tor j tor eta I nu k, tor k. That's what the thing looks like. And when you work that out, oh, I forgot the minus sign, so that's still there. When you work that out, there's a nice identity when you in this codimension 1 case. If you take the jth derivative, ordinary spatial derivative, of the jth ordinary partial derivative with respect to the jth coordinates, notice these nu k's are well defined globally, not just on the manifold, because it's grad f over length of grad f. You can take dj nu k. You find that that's the same as 1 over the length of gradient of f times this matrix eki di fj. You get second partial derivatives. But these are ekis crop up again when you take this guy. So we can write this as minus eta I eij eki di fj di fj and times tor k. And we're interested in the trace of this, so the mean curvature is h, which is the sum from I equals 1 up to 2n minus 1 of tor I b tor I rather, and this is h at a point xy, and this is the second fundamental form at the point xy. And in this case, that turns out to be, let's see, it's ei. This is a matrix of an orthogonal projection. So actually, I shouldn't have got that. This is KL DL, and then J I, right, DLFJ. So I'm taking both tor and eta are going to be both tor and eta are going to be the tor I, and then we're summing on I. Maybe I should use a different index here, Q. Tor Q. Okay, I seem to be making a long story out of this, but it's rather simple if you do it the right way, which I probably did not do. But then this can be rewritten now. Tor. Let's see. We'd better use superscripts for the eta and k, otherwise we'll run into trouble with these guys. So eta I, tor k. Okay. Superscript. Okay, good. So then this is TQ I, TQ K, EIJ, EKL, DLFJ. Okay, now this, remember, is the matrix of the orthogonal projection again. That's our standard expression for the matrix of the orthogonal projection. When we sum it, at least from 1 up to 2n minus 1, sum over an orthonormal basis, you always get the matrix of the orthogonal projection. So we get an EIK, but that contracts with this because the square of the projection matrix is equal to itself, right? So this becomes EIJ. In fact, it contracts twice. because first I contract this guy to get an EIL, and then I contract that pair to get an EJK, to get an ELJ. So we get an ELJ DLFJ over grad F. Okay, so that's the expression for the second fundamental form, and I think I've forgotten the minus sign again. Like so. And so we just have to compute this. Well, you see, when you compute this out, this is just, well, ELK, here's ELJ. It's the identity minus nu I, nu j. So the identity bit just gives us the Laplacian. So this is minus the Laplacian of f, the ordinary Laplacian in R2n. And we've got this factor 1 over grad f. And these other terms, when you work them out, are the same as nu I, nu dotted with the gradient of grad f. I'll leave you to check that that's the correct expression for that, and that takes care of this 1 over grad u thing too. No, actually it's nu grad f over grad f, right? So yeah, so the delta ij part gives the Laplacian, and the other bit, the nu I nu j bit, gives nu dotted with the gradient of the length of the grad f. And we can compute that in this example. Let's see. The gradient is here. It's the gradient. And the length of grad f is just r, square root of x squared plus y squared. So the gradient of the length of grad f is just x, y over r. So here we get, and what about the Laplacian? Well, the Laplacian is clearly 0. Just take the divergence of this vector. Laplacian of f is the divergence of this, right? The divergence of this gives a factor of n here and a factor of minus n here. So it's n minus n equals 0. So this Laplacian part is 0, and I claim this part is also 0. Let's check that. Notice that this vector xy over r is orthogonal to this vector. So indeed, that bit's also 0. So indeed, that is the correct claim. The sigma is minimal in R2n minus 0. That's good. And yeah, it's minimal in R2n minus 0. Now, I claim it's also stationary in R2n. Sigma is stationary. That means it has first variation 0. Stationary in all of R2n. Well, in fact, if you did this week's homework, you'll know that that's true, because that was problem 4.5, right? Of this week's homework. We checked in problem 4.5 that if you're in this kind of situation where you've got a minimal submanifold and it's minimal, zero mean curvature, except at an isolated point, then in fact it's stationary everywhere. So this is an example of a stationary rectifiable multiplicity 1 here. Notice there was no multiplicity function, meaning that it's identically 1. So this is an example of a stationary multiplicity 1 rectifiable varifold in R2n, which has an isolated singular point at the origin. Okay, so I wanted to do that because I forgot to do that last time. So now let's go back to make a start on chapter 6, theory of currents. So the first thing we have to do is a little bit of multilinear algebra, which is not too unpleasant. So multilinear algebra. So let's begin. So we're going to be in some high-dimensional Euclidean space, say Rp, with the usual orthonormal basis, E1 up to EP. And I'm going to let lambda 1 of Rn be the set of linear functionals. Real linear functionals on Rp. Functional means real valued, right? That is omega Rp, set of omega Rp to R, which are linear. So that's omega 1. And let's take a basis for these, which is dual to this. So take a dual basis. So we're going to use this classical notation, which looks a bit funny at first sight. So the dual basis, that is the basis for this space, which is dual to these guys, is the dx1 wedge dxp. It looks like they're variables, but of course they're not. They're just linear functionals on Rp, and the definition is that they're linear, they're in this space, and dxj of ei should be the Kronecker delta ij. So it's a classical, I mean, we're not going to change the notation now. That notation grew up historically. It's a sort of a funny notation, but once you get used to it, you don't notice it. And so that's the space of functionals. And then we want to define the space capital lambda n of Rp. Well, to be for completeness, let me also define what lambda 0 of Rp means. That just means the reals. It's the field in the question, which is R in this case. And lambda n Rp for n bigger than or equal to 2. Lambda n of Rp is the space of so-called alternating n-linear functionals. Any n-linear functions, alternating, I'll explain this, alternating n-linear functions on Rp. In other words, that's the set of omega which map you from from n copies. N-linear means linear in each component. So we're looking at n copies, taking the Cartesian product of n copies of Rp, n factors, into R, and should have the property that omega of V1 up to Vn should be linear in each component. Notice that's a lot different than saying it's linear. It's not linear. It's linear in each individual slot, right? So this is linear in each Vj. J equals 1 up to n. All of these Vj's are in Rp. And the other thing is what's this alternating. That means that if you flip two of these, so if you take omega V1, Vi minus 1, Vi, Vi plus 1, Vj minus Vj. This gets a little tiresome after a while. There should be a better notation for that. And if you flip the I and the j, so this is the ith slot, and this is the j slot, and if you flip these and leave everything else fixed, it just changes the sign. It doesn't change the value otherwise, just changes the sign. So this is omega, here we go again. Vi minus 1, but now there's a Vj in the ith slot. Vj minus 1, and now there's a Vi in the j slot. So that's the definition. We look at the set of all of those things. That's called lambda superscript n of Rp. The alternating n-linear functions on Rp. So, and notice one important consequence of this: if any two v's are equal, then of course omega must vanish, because it would have to be the negative of itself in that case, right? So Vi equals Vj, where I not equal to j, of course, implies omega V1 up to Vn equals 0. Okay. So, of course, that's ridiculous. You've got to try and work out what these things really look like, right? I mean, you can't do mathematics in an abstraction like that. It's just nonsense, right? So we've got to work out what they look like. So let's see if we can work that out. What's that? Alternating means if you flip any two, you get a change of sign. You first, you're worried if you get a different answer if you flip two that are non-adjacent, as to from flipping two that are adjacent. It all works out. That's the definition anyway. And we really got to work out what these things look like. So let's see if we can do that. So let's take one of these omegas, see if we can work out exactly what it looks like. V1 up to Vn. Well, remember these vectors in Rn, so Vi can be written as a sum using the standard basis, sum j sub I, sum from j equals 1 up to p of Vij Ej. So we can write it out that way, but now we're going to run into trouble notationally, so we'd better call this dummy variable here j sub I, to emphasize that it's a different name for each I, right? So this is for I equals 1 up to p, up to n. It's 1 up to n. By the way, I should have mentioned, notice because of this property, because of that property, notice that lambda n Rp is equal to 0 definitely if n is bigger than p. Well, I'll come back to that point in just a second. Maybe it's better to do this first, make it clearer. So let's agree to write these out in terms of their standard basis vectors. So then this becomes a humongous sum with p to the n terms, right? It's the sum over all indices j1, j2, jn between 1 and p of omega. And remember, omega is linear in each Vi, so I can pull out the sums outside. That's okay. So we'll get these multiple sums coming outside, and I get Vj1, V1J1, V2J2, up to Vnjn, and what's left inside is omega Ej1 up to Ejn. So that looks like a complete mess. And, but then we can make one observation. Notice that if any of the indices j are equal here, we'll get an equality of 2 entries here. And that'll make this 0. So we can certainly certainly stipulate that j1 up to jn are distinct, because all the other terms are 0 because of this alternating property. So you can you can drop all the other terms, they're all 0. Okay, that's good. And now we've got to work out how to sum this in a sensible way. Well, one nice way to sum it is to first select indices which are ordered. Of course, these indices are not ordered. We've got to sum over all possible indices, regardless of which one is bigger than the other, right? But just take, for argument's sake, just take some ordered indices to begin with, j1 up to p. And then we'll get the full sum if we first of all look at one of these, and then look at all the permutations of the indices here. There will be n factorial terms for each such choice, and then finally sum over all of these. That would get all the terms exactly once. So let's introduce the correct notation then. So let INP be the set of these indices. Which are correctly ordered. J1 bigger than or equal to 1, less than J2, and so on, less than Jn, less than or equal to P. Okay, good. So we can do that, and then I claim, as I said, that one way to sum this, a nice way to sum this is, first of all, just to fix one of these. So then this is sum over, and then we sum so we choose one of these first. Then we permute the indices, that's n factorial terms. So we take sum over all permutations sigma. We're permuting the indices only, the subscripts. So that's permutation sigma of n entries, right? Sigma of the entries 1 up to n. There are n factorial of those. And then we take V, the same thing, V1, J1, Vn, Jn. Yeah, so as I said, we want to permute these around. So I want Vj sigma 1 up to Vj sigma n, and then omega of Ej sigma 1 up to Ej sigma n, like that. And I forgot, we've got to keep track of these. Oh, there they are, there. And then we've got to sum over all J1 up to Jn in INP. That's these guys. Okay, good. Now, that still doesn't look too great. But on the other hand, notice we can do something here. This is a permutation of the basis. This is a permutation of Ej1 up to Ejn. So I can rewrite it as omega Ej1 up to Ejn. It's just that I've got to work out the sign. Well, each time you make a transposition, it changes the sign once. And as you recall, the number of transpositions to get back to the standard ordering is called the sign of the permutation, right? That's the definition of the sign of the permutation. So this can be rewritten as sine of sigma, which is plus or minus 1, depending on whether you get an even or an odd number of permutations, and however many it takes to get back to J1 up to Jn. There we are. So that's that. And so that's looking a little better. Still not great, but At least it's looking like maybe we're getting somewhere. And yeah, so what else can we do? Well, we could label these guys alpha. So multi-index notation. So let alpha be these n tuple j1 up to jn. And then we could call this omega sub, it's just a number. This is a number. Let's call it omega alpha. So then this is sum over alpha in I and P, sum over perms, sigma of 1 up to n, and then Vj sigma 1, V1 j sigma 1, V2 j sigma 2, Vn j sigma n times omega alpha. Just a number. Omega alpha is the number omega ej1 up to ejn. And now we can do some notation. Notice that this, right. Okay, so remember we had these dual forms here. And so I want to further simplify this, but I've got to introduce a little bit more notation first now. So, oh, sorry. Sine of sigma. So I want to I want to finish this discussion, but we're lacking a little bit of notation, so let me introduce that. So remember we have these forms, dxj, the dual basis, dxj ei equals delta ij. Notice that dxj of v, since v is equal to the sum on I of vi ei, then dxjv will just pick out the jth component, vj. And we can define there's a sort of a nice way of getting these of these alternating forms, and that is to use the following notation. If you take omega j to be one forms, yeah, well, I'm calling them forms, but they're not forms yet, actually. Forms have got variable coefficients. We're just at the linear algebra level at the moment. So this is in the dual space, omega 1 Rp. Then you make a definition. Omega 1 wedge up to omega n. I want to define that as one of these alternating n linear things. Namely, I've got to say, so if I want to define it as one of these things, I've got to say what it does to vectors v1 up to vn, right? So I've got to say what that does. Vectors v1 up to vn. Well, I want that to be sum over perms, again, sigma of sine of sigma times omega 1 times v omega 1 omega j sigma 1 v1 times, etc. These are products up to omega j sigma n. So again, we're permuting the indices. This time of these indices, w1 up to omega 1 up to omega n, vn, like so. By the way, notice that we recognize that, right? That's exactly the determinant of omega j, omega j vi. It's exactly the determinant, omega j vi. But it's better to write it this way. The omega 1 up to omega n. And so that's our definition. Notice that is indeed one of these alternating n linear forms, right? Because it's clearly linear in each v. For instance, it's trivially linear in v1, because the only place v1 appears here is in that first slot. And omega j is a linear functional, right? So it's trivially linear in v1, etc. And it's trivially alternating, right? If you flip two, that's one of the properties of determinants. If you flip a pair of columns, then it changes the sign of the determinant. So that is indefinitely, this is definitely one of these things in lambda n Rn, like so. But in particular, if we take dxj1 wedge up to dxjn, which is just a special case of this, then this looks like the sum over perms sigma of sine of sigma, then omega, so dxj, so this would be, now remember dx, where is that? Here. dxj hitting v is just vj. So this will be v1j sigma 1, v1j sigma 1 times v2 j sigma 2 times, etc., up to vn j sigma n. That's what that'll look like. This is dx1 hitting v1 up to vn. I left out the v1 up to vn. But stare at that for a second and then look back here. It's exactly the same expression, except for the omega alpha, which can come out the front here. So this can indeed be rewritten in a way that looks much more palatable. So this expression now becomes sum over alpha equals j1 to jn in INP. And then it's omega alpha comes out the front. And then it's a dxj1 wedge up to dxjn hitting the vectors v1 up to vn. Same expression, notice. So in other words, if we drop the v's, that is, this is rather nice, that now any omega in lambda n and lambda n of Rp tells us that we can always write omega equals the sum over alpha equals j1 up to jn in INP of omega alpha times dx alpha, where dx alpha is abbreviation for dxj1 wedge up to dxjn. So now that really looks very compact, and furthermore you can say what the omega alpha is. Omega alpha is just omega at ej1 up to ejn. So that's, now you really see what these things look like, or at least you convince yourself you see what they look like. You forget that this is a complicated quantity, and you just see this is a rather simple quantity now. Very nice way to think of the things in lambda n. Okay, so that's good. So now we know what these things look like. Now, let's get a couple of properties. If you take omega alpha dx alpha, so you take one of these in ILP, and you take another one in MP. Oh, by the way, let's go back to this point that I made before. Notice that it is clear now that clearly lambda q RP is trivially equal to 0. It's just the 0 element if P is bigger than, if Q is bigger than P. Because there has to be one repetition in this wedge. And there has to be one repetition here. Doesn't matter how you arrange the sum, there always has to be at least one repetition in this coefficient, which makes all the coefficients 0. Okay, so let's see. Let's take two of these, one with n equals L and one with n equals M. Say eta beta dx beta. And then you define, so call this one omega and this one eta. And then you define the wedge product of these. Omega wedge eta equals sum alpha and beta of the product omega alpha times eta beta times dx alpha wedge dx beta. Notice this makes sense. This means dxj1 wedged up to dxjn, and this one means dxi. Well, there's a little bit of a notational no, there's not really a notational problem. It's just that there's no problem unless you make one. And notice that a lot of these terms could be 0 if there are any repetitions of dx alphas, dxj's appearing there. And one thing you've got to be very careful of, notice this is not, you've got to be careful about writing it in the reverse order. What's this one? It's got the same coefficients, at least, except for a sign, but then I want to take the dx betas and put them out the front here. Now let's see. You've got to keep in mind what these really are. This is dxj1 wedge up to dxjn, this jl, this first bit. And then the second bit is dxi1 wedge up to dxim, right? That's what that really looks like. And then I want to take the dxi1 and put it out the front there. Well, each time I cross, I get a minus sign. So I get a minus 1 to the L in getting the dxi1 out to the front. Similarly, I get a minus 1 to the L then getting the next one out to the front. So what's the change of sign then? We get a minus 1 to the L every time we do it, and we have to do it m times. So it's minus 1 to the L times m times the original ordering. So that's something to be careful about. The sign might change. If L times m is odd, the sign will change. And of course, it's associative, trivially. Trivially, that's correct. So, so now we've got a wedge product, and of course, there's no conflict of notation here. You can check that there's absolutely no conflict of notation. dx1 wedge dx2 means the same thing regardless of whether you take this as being a formal quantity, the way we were originally introduced it, or whether you use the definition of wedge product of two one forms. Same thing. So there's no conflict of notation there. Okay, so that really makes things much easier to handle now. And, so everything looks rather simple. And there's a couple more concepts that we need before we do something interesting. And yeah, we'll take a break now for 10 minutes, I guess. Do you by any chance have a tissue? I didn't bring a tissue with me. Oh, it's okay, I've got one. Yeah. Oh, yeah, I got a, I don't know what's wrong with my throat, but it's okay. No, it's just some, I don't know what. Possibly something dreadful developing, but I don't know. Oh, no, I've had this on and off. I always get this thing. I don't know what it is actually. If I went to a specialist, he'd no doubt come up with some fancy explanation, such as you're dying.
Mosquito, is it bothering you?
They haven't bothered me for the last few nights. It was just that one night. It was a strange coincidence. You mentioned it the night after they'd driven me crazy. Just one mosquito.
Okay, but now it's okay.
Since I haven't had a problem.
I think maybe it has to do with it was raining a lot, like
Right.
and then so there are some mosquitoes.
Yeah. Anyway, I've had no problem, so I'm not going to do anything about it until something happens.
So we are thinking maybe we need to buy you a mosquito net.
Let's wait and see if it.
High-tech mosquito killer.
Well, well, I did. I got one the other night. I used my hands though. I felt no compassion for it. I felt ashamed of myself. No compassion at all.
I had another extra one that they make some sound, so they just keep them away. But I don't know. In fact, I did not feel it. I do not feel it when I get into sleep.
Okay.
But I don't know whether it will bother you.
Yeah. See, that's what's so maddening about these things. They're not that worrying, but you know, as soon as you go to sleep, they'll start getting on you and sucking your blood. Yeah.
So do we want to arrange something on this Friday? So Bob is arriving on Friday morning.
Right.
But it's too early, so I think he said he will stay in the airport
Yeah.
to get some whatever.
Right.
And then he will come
Yeah.
to maybe my department. Or I want to find
Yeah.
a hotel for you. I said
Yeah.
no.
Yeah.
But so he probably will stay in some office.
Right, but we should take him out to dinner at some cheap place, not an expensive place. Bob hates expensive restaurants.
So he less than $200.
He just hates it, even whether he's paying or not. He just hates it.
How about the McDonald's?
No, thank you.
But for the place, remember the other day?
Yeah.
That's really cheap.
Oh, that was really cheap. But that's maybe we don't have to be that cheap. Anyway, why don't we take him out to dinner?
Yeah. We should go.
Yeah.
I was supposed to go to dinner. No, this Friday. So then and then I could drive him after the dinner. I can drive him to his
Right.
apartment.
Okay.
Where is his Airbnb?
He made a reservation by himself. He just didn't tell me anything. I have done that.
Near the university, right?
No, it's in Xindian.
In
But
Xindian?
it's nearby
Nearby
the MRT metro. Yeah. So he like bike. He also check it out. He says
So he can buy
it's
from
a
there.
new bike he can rent and then.
Yeah, he can buy. It will be like 20 minutes from there.
I don't know, but for safety reasons, I think I just suggest him to take the metro.
But he can walk. But if he walk is not safe either, because sometimes there are lots of bikers. They bike pretty fast on the trail.
But anyway, but that's one thing. But on the other hand, maybe we could do, or we could later. I mean, in fact, this weekend I went hiking with a friend. I thought about inviting you, but I worry about because they say it's going to take 6 hours.
Oh yeah, no, that would have been a bit much for me. Right.
Even there are some places you have to give me roads.
Right. Okay. I'm glad you left me in peace then.
But it's very close by the place we went last night.
Yeah. Let's take Bob on a gentle walk, possibly. Right.
Yeah.
Maybe in 1 or 2 hours, or even 3 hours. if he's up for it. Better check that his knees are okay and so on.
Yeah.
He's a big guy, and I know he was having trouble with his knees at one point.
Yeah. So I don't know.
Yeah.
Recently.
Yeah.
If 1 hour, 2 hours, maybe the one next to the university, So there's one, just a couple of stops.
Right.
There are several.
Fairly gentle.
Yeah, very gentle. There are several very gentle ones just nearby our campus.
It's gentle for missions.
Right.
For others. Probably they have some part is easier.
Yeah, there are some easier parts. Some of them are more difficult. I just didn't realize before this weekend. I mean, there are several attractive ones. It looks quite. So one of them I look at from this side. They say it's a much smaller scale of the trail you went with Mao-Pei. So
it's along the sea coast, right?
Yeah.
Yeah, already went to the festival.
Okay. All right. Yep. Well, before we make a decision, let's find out about Bob's condition, in particular what his knees are like.
We
Yeah.
should definitely go to a different first, and then we can talk. We can discuss what we could do.
Yep. Okay, so let's continue. So, so we saw that lambda n of Rp then is just equal to the set of sigma omega alpha dx alpha. set of omega that can be written in that form. Alpha in I and P. Okay, and we need a little bit more, a few more preliminary results about this space. One is that if you take a linear map from Rp to Rq, linear, then and you take an omega in this space, lambda n of this space, then you can define something called the pullback of omega. And the claim is that that's equal to, that's in the space back here. So you're taking a lambda in, an omega in this space and pulling it back to an omega in this space. And the definition is, we've got to say what it does to vectors. Remember, these are alternating n linear vectors, so we've got to say what it does to vectors v1 up to vn. And I've got to define it in such a way that it's alternating. Well, simply define it to be omega hitting the image of v1 under L vn. It's clearly linear in each vi, and it's clearly alternating. So this is indeed in this space. And let's work out what, remember, all of our omegas can be written in this way, so we should work out what what the pullback of those guys are. That would be good to know. So let's work out L sharp. So in particular, L sharp of dxj1 wedge up to dxjn, well, hitting v1 up to vn, well, that's equal to dxj1 up to dxjn hitting LV1 up to LVN, like so. But then that, remember, we've got the expression for this. We know what this is, what the definition of this is: sum over perms, sigma, sine of sigma, and then you've got to take dxj sigma 1 hitting LV1, this gets a bit complicated, times, etc., up to dxj sigma n hitting LVN, and that's dxj sigma 1 just picks out the j sigma 1 component of L. Remember, L's a mapping into Rp, so that means L has got components L1 up to LQ, mapping into RQ. So that means that this just picks out the j first component. So this is Lj sigma 1 hitting Lj sigma 1, that component. It's a linear map. Each of these components is a real linear map, right? So V1 up to Lj sigma n Vn, like that. That's what that looks like. And oh, I forgot the sine sigma again. sine sigma, summing over the perm sigma. And that's exactly the wedge product LJ1 wedge LJN by definition. We find this in exactly this way, using the perms like this, hitting V1 up to Vn. So when you decode that and take out the V, we started off with this. L sharp hitting V is equal to that thing over there. So in other words, you end up with a nice compact statement. That is, L sharp of dxj1 up to dxjn is actually just equal to LJ1 wedge up to LJN. Like that. Very nice. This could, I suppose, alternately be used as an alternate definition, but it's better to keep things definite like this. This is the definition. And then as far as practical use is concerned, this is probably the convenient thing to use. Okay, we needed to say that. Now there's also, we've got to talk about n vectors. These are covectors, these things in lambda n. N covectors, alternating n linear functionals. We also want to talk about n vectors, but we don't need to repeat everything. So we could, if we really wanted to be formal, you could repeat this whole discussion starting with lambda 1, starting with lambda 1 of Rp in place of Rp. And then you'd get lambda 1, lambda n of lambda 1 of Rp. But you don't want to get into that. You want, so let's think about the dual space of this. So these guys are dual to, so you've got Rp with the basis vector Ej, and then you've got the dual basis. Which is dxj. And then you could talk about the dual of the dual, but you don't want to get into that. That's too annoying. So we'll identify, we think of the dual of dxj as being Ej again. That's only a sort of a change of notation. And so instead of looking at this, you'd be looking at lambda n of Rp. And these guys would be, instead of looking like linear functionals, they'd look like vectors. So then you repeat the whole thing with this identification. I shouldn't have crossed that out. I mean, we're really doing that, except that we're making this identification. Again, we're considering alternating n linear forms, but we're thinking of these guys now as the duals just being vectors, Ej. So that, if you think about it, that leads to the space that we call lambda n Rp, which is the space of n vectors. N vectors, which can be written analogous to these guys. Analogous to these that can be written that way, except that now we'd be using vectors instead of dxj's, or we're actually technically looking at the dual of the dxj's, but we're identifying that with Ej. So then so that's the set of eta such that eta can be written as the sum of eta alpha, alpha in I and P again, omega alpha E sub alpha, where E sub alpha is Ej1 wedge up to Ejn. And this is defined exactly, it's really this space, but we're identifying, this would really be, technically this would be really dxj star, right? And this would be dxjn star, but nobody's going to do that, right? So it's much better to think of these as wedge. So anyway, that's the way it's defined formally. So now we know what these look like. All the expressions that we derive will be the same. These will still work, same as before, and so on. So you don't have to repeat the whole thing to get the k vectors. So let's assume we've done all that. So now we've got both covectors and vectors. And there's a dual pairing between these. So lambda n can be written as the set of all Rp, set of all omega equals sum omega alpha dx alpha, and lambda sub n Rp can be written as the set of all omega equals sigma eta alpha E alpha, where dx alpha is dxj1 wedge to dxjn, and E alpha is ej1 wedge up to ejn. And here alpha is, each alpha is j1 up to jn in INP. Now clearly these guys are a basis for this space. There's a linear space and these guys are a basis. So dx alpha, so these are the basis for this first space. INP. So let's see, I've forgotten. What's the dimension of that again now? What's the number of elements in INP? It's P choose n, isn't it? Yeah, P choose n. So the dimension is P choose n. And likewise, this one, basis for this space, similarly. So that's equal to the dimension. Okay, and now these covectors we found that you pull them back, right? Vectors you push them forward with L. So, well, before I do that, let's finish this discussion. So they're our basis, and you can define an inner product. It's the inner product induced by the inner product in Rp, of course. So the inner product for lambda n Rp, simply, well, it's the obvious inner product. You take this guy, so you take omega wedge eta, let's call it dot. Omega dot eta is just if eta is equal to sigma eta alpha dx alpha, then you simply take the sum of the alpha in INP, omega alpha eta out of alpha. And likewise in lambda n subscript Rp. Same thing, except that we're working with these. But the definition of the inner product is the same. And there's also a dual pairing between lambda superscript n and lambda subscript n. Dual pairing. if you take omega equals sum alpha NINP omega alpha dx alpha, and eta equals sum alpha NINP eta alpha E alpha. So these are n vectors, these are covectors. The dual pairing, which we denote omega eta, that's just, in fact, it's usual to write it the other way around. It'd be convenient for us to write it the other way around. So eta omega is just, again, this sum. Eta alpha times omega alpha, like so. So you've got all those things. Now, let's get back to pushing forward and pulling back. So we know that we can pull back these covectors, and you can push forward. So again, we've got a linear map, same as before. Here it is, linear map, RP to RQ. Then linear. Then, and you take a eta sum alpha NINP eta alpha E alpha. This is in lambda sub n RP. Then I want to say what this is, the push forward of eta. That's supposed to be one of the n vectors in RQ. And the definition is, it's defined by eta, L sharp eta. Now, let's see, to define it, I have to say what it does to vectors. So V1 up to Vn. Well, that's just eta L sharp V1 up to Vn, L sharp, Vn. Oh, yeah, that's right. And you can check that this is exactly dual to the pullback. If you take the dual pairing here, like this, then L sharp omega paired with eta is exactly the same as omega paired with the push forward of eta. This is for eta, for omega in lambda superscript n RP, and for eta in lambda subscript n RQ, RP. Oh, omega is in RQ, sorry. Yeah, so it's all, you can check that. It's simple, just a couple of lines of computation. So I think that's as much as we need to say about the linear algebra background. Now we should talk about forms. That's the main thing, because in order to talk about currents, you have to talk about forms. Because currents are linear functionals on the, are continuous linear functions on the forms. So let's talk about forms. So U is going to be open in RP, open, and you let ENU, well, first of all, E0U is just the space C0 of U, the continuous functions on U. And then for n bigger than or equal to 1, ENU is equal to the space of forms. In other words, that's a set of omega, which can be written sum over alpha in INP of omega alpha dx alpha, where now this is a C infinity function on U. It's no longer a constant, as it was there. So this is omega alpha in C infinity on U. Oh, sorry, these are supposed to be smooth forms, so this is C infinity. The C infinity functions. E0 is the C infinity functions on U. And likewise, the n forms are those that... So what does that really say? That means that ENU is the space of C infinity functions defined on U with values in lambda n Rp. That's all. So that's what we mean by forms. And then for us, a much more important space is the space Dn of U. That means the elements in this which such that each omega alpha has compact support. So this is the set of omega in ENU such that omega equals some omega alpha dx alpha, alpha in INP, such that each omega alpha is C infinity with compact support. Okay. Now we need to do a little bit of algebra again with these things. Oh, by the way, I made a notational thing here. It's of course, it's conventional to write these guys with superscripts, so that this dual pairing looks like this. Just a notational point. Okay, so let's see what we need with these. So they're the definition of forms that we're interested in. Now, yeah, we need to talk about a couple of points now. Exterior derivative in particular. Yeah. Oh, I don't think I want to erase that. So take a omega in En U and define d omega. So omega equals some alpha in INP d omega alpha dx alpha. So this is a C infinity function on the set U then. And d omega is defined to be the n+1 form that you get by taking the sum over alpha, and then you take the differential of alpha and wedge it with dx alpha. Notice that I can write that out a bit further using the chain rule. We can compute this differential. So we're using the usual notation here that if f is real valued, df is the one form that you get just by taking the differential. So df is just the sum j equals 1 up to n partial jth partial of f dxj. It's a one form. Usual meaning of df, but that is a one form, notice. Fits into our description because it's got a dxj. It's one of these guys. When n is equal to 1, it's one of these guys, and it's got coefficient dj f, which is a C infinity function. So it's one of these things. It's a one form. So the differential of a real valued function is indeed a one form. And that's what this is. So let's just write this out, though, in terms of this chain rule. So this is sum over alpha in INP dj omega alpha dxj wedge. dx alpha. So indeed, that we recognize that is definitely one of these things in En plus 1 of u. It's a C infinity function times one of these dx betas, where the index is in the n plus first order of n plus 1 rather than n. So indeed, it's En plus 1. So d is an operator that is linear. It takes you from ENU to En plus 1u. And notice this guy is E0. This also is consistent with the notation here because this is in E1 u. So it also works when n is equal to 0. So this is for n bigger than or equal to 0. And of course, keep in mind that all of these spaces are 0 if n is bigger than p, right? Okay, so that's the definition of d. Now notice that d squared is 0 because terms cancel out. If you compute, so we've got to take d again. So d squared omega is d of this. Like so, and we just got to take d of that by definition. So that gives us some and then I take d of this. But d of this, remember, is by the same reasoning as we had here. This is di dj omega alpha, second partial, times dxi wedge dxj wedge dx alpha. So that's what that looks like, sum over alpha. And of course that's 0 because the mixed partial derivatives are equal. So 0. So d squared is equal to 0 as an operator. It's equal to 0. Okay, now we can also pull back forms. So let's talk about that using this. So if you've now got a mapping f u into v, C infinity map, then you can, and you take a form over in this space, then you can define f sharp omega. And let's define it. It's going to be, so omega is sigma omega alpha dx alpha. So this is going to be, I'm going to define this to be sum over alpha in I and P. And then I'm just going to use this definition. I'm going to take the form evaluated at f of x, that's the image point. Oh, that's right, the image point. That makes sense because omega is E and V. And then I'm going to pull it back by the induced linear map. So I'm going to use L equals dfx sharp of omega, like so. Now, that's the intrinsic definition without even writing it out. That's what the definition is. So that's the definition. Now we've got to check that it really works out. Notice this makes sense because we're back in this linear, linear algebra setting where omega restricted to a point is just one of the n forms in RP, n alternating n linear functions in RP, and this is just a linear map at a point fixing x. So this makes sense, but we've got to check that it gives us something back in the E and U here. So let's check what this looks like. Well, omega, remember, is this. So this is dfx sharp, and then it's omega alpha at fx. It's the composite, and then dx alpha. But according to this, that's the same as, so let's call this star. So here I'm using star. That's just omega alpha fx, and then it just picks out the relevant components. Remember, this is dxj1 up to dxjn, really. So this just picks out the j first component of that. So it's just dfx dj1 fx wedge, just using this star literally, wedge dfjn at x. Now that makes sense. dfj1 is a map, a linear map from rp into rq, right, at each point x. So it's exactly the setting we were talking about up there. So in other words, we get, so this is the definition, and in